Hi everyone, this is Jude, and today I'll be presenting my orthogonal families of curves project for my differential equations class. Let's start with the family of curves and what even it is. A family of curves is just a group of curves that are described by one general equation with a parameter like the letter a. For example, here we have y equal a square root of x, and a every time a is a different value, we're gonna get a different curve. So that's basically what it is. So this is our first family of curves. Now let's see how we can describe this family using a differential equation. Instead of just using the original equation, we can describe this whole family with a differential equation starting with by using y equal a square root of x. And we're going to find the derivative of each side. So y is going to become dy over dx, and a square root of x is going to become a over 2 square root of x. And then after this step, I'm going to solve for a from using this equation right here. So a is going to be equal y over square root of x. Then I'm going to plug that value into here. So that's how we find the differential equation for the family. Now let's find the orthogonal family to this one. To find the orthogonal family to the differential equation, we need to first know what an orthogonal family is. It's basically two curves that are orthogonal if their tangent slopes are the negative reciprocal. So as you can see right here, our original equation was dy over dx equal y over 2x. And to find the differential equation for this orthogonal family, we're going to flip the differential equation and change its sign right here. So we flipped it, so we put the 2x in the numerator and the y in the denominator, and we changed the sign to a negative sign. So this right now is our differential equation for the orthogonal family. Next, I solve the new differential equation to find an actual shape of the orthogonal curves. So right here we have this orthogonal differential equation. I rearranged it so that I have the y on one side and the x's on one side. And then after doing that step, I solve the integral for each side, multiply both sides by 2, and we get this result, which is c equals y squared plus 2x squared. And this is our equation for the orthogonal family. So after getting that step, now I can use both of those equations that I found. The original one is up here, and then the one we just found is down here. As you can see right here in these graphs, this is the graph for when a is equal to 3, and this is the graph when a is equal to 2, and this is the graph for when a is equal to 1. And right here, I included a picture of all of them together, so we can actually see them all in one picture. So actually, if we say this ellipse right here, the red one, is actually orthogonal to this blue one, and it's orthogonal to this black one. So both of them don't need to have the same a number. They can be different numbers, and they're still going to be orthogonal to each other because that's how the equations work. They're the reciprocal of each other, so they're always going to be orthogonal to each other. Right here, I also have this little picture where I zoomed in, and as you can see right here, the angle is perpendicular. So I decided to go a step further and explore a second family. For the second example, I used y equals ax to the fourth, and I went through the same process where I solved for a, and then I plugged it into the equation, and I ended up with dy over dx equal 4y over x. Now let's find the orthogonal family for this one too. Just like before, I took the negative reciprocal of the slope, so dy over dx equal 4y over x. I'm just going to basically flip it. So x is going to be in the numerator, 4y in the denominator, and the sign is flipped. So now this is our orthogonal family for the second one. After finding the differential equation for the second orthogonal family, I went and did the same steps we did earlier for the first one. So I put the y's on one side and the x's on one side, and I integrated both sides, and then we added a 1/2 x squared to each side so we can have c by itself. And now this is our second orthogonal family. Here you can see the graphs for y equal a x to the fourth, and its orthogonal ellipses. Again, the original curves and the orthogonal curves interact at right angles. So right here, this is a right angle, this right here is a right angle, right here it's a right angle, and it's kind of the same thing as the first one, but this time we have a different shape, kind of, and a wider ellipse, as you can see in the picture. Both orthogonal families ended up being ellipses. The similarities is that both intersections are perpendicular, so both of them pass that, and the ellipses are different shapes because the original families were different. So if they were the same, the ellipses would be the same, obviously. Now for y equal a square root of x, its ellipses led and stretched more along the y-axis, whereas y equal ax to the fourth led to ellipses stretch along the x-axis. In this project, I showed how families of curves can be described by differential equations. Finding the orthogonal families means taking the negative reciprocal of the slope. Solving a differential equation will give you the orthogonal family, and orthogonal curves are perpendicular at point of intersections. Also, different types of original curves could lead to similar orthogonal families. So the main idea of this project was to take a family and make it into a differential equation, then solve it and find the negative reciprocal. Thank you for watching.